Welcome everyone to the first edition of the spring session of the One Word Probability Seminar 2026. We are very happy to have you with us today. It's a real pleasure to introduce our speakers, Marcelo Campos from IMPA in Rio de Janeiro and Simon Griffiths from PUC in Rio de Janeiro, who will talk about probabilistic aspects of Ramsey theory. Marcelo, Simon, thank you for being here, and the screen is yours.
Well, thank you. So I'll be going first, and then Marcelo will give the second talk. In a way, they're quite closely related. I think I'm going to take more the task of sort of, introducing a lot of the way we think about lower bounds in Ramsey theory and giving lots of examples. And in the second half, I'll talk about something slightly different. But that in the first half, at least, is sort of a preparation mentally for at least so some of the things Marcelo is going to talk about in his talk. So there is that relation or that connection through the talks. So I'll put up my slides. I'll mostly be on the slides. If I've got a bit of time at the end, I'll do a little bit on the board behind me. This is when I just asked some AI to do a multicolored graph and make it very colorful. So that's what happens if you do that. Sort of making it full screen for me. Okay, let's see. No, I've done it wrong. Okay. So I'm just trying to make it full screen for me, and I've got all these different things. You can see we're at practice with I think that's okay, right? Although I'm sliding it instead of. Okay. Right. So let's get. Okay, I'm sliding. Okay. Let's get started then. What is Ramsey theory? I'm a bit confused by this thing. Where's the. Sorry, I'll just. So anyway, I'll keep talking and I'll mess around. So Ramsey theory is basically the theory of inevitable structure. So in all sorts of places in the world, you can see systems that look to be very disordered. Any kind of thing can be happening. And yet Ramsey theory is the study of being able to find within there some inevitable structure. And there's about 1 million different contexts in which you can talk about it. We're going to really be focusing more on graphs, but I wanted to mention that you can do this in various arithmetic situations where you find a sum all in the same color if you color the integers, or solutions to equations in general, or finite sums or subspaces. Euclidean Ramsey theory. There's a whole world out there of Ramsey theory for anyone who wants to go and look into it. So who was Ramsey? Ramsey was a young guy back in the 1920s, and unfortunately he died very young, but in his short time he managed to make contributions to philosophy, economics, and mathematics. And he said things like, "I hope you like red-blue colorings." It's the kind of thing he said. For example, if you color all the pairs of integers, so for every pair of integers you assign either red or blue, then he showed you could find an infinite set within the integers in which all of the pairs are joined in the same color. Now, that's obviously an example of this structure thing. You start off with something completely arbitrary, a red-blue coloring of pairs of integers. It could be any such coloring. And yet you find within there a very large, an infinite, in fact, set, which is incredibly structured. All of the pairs have the same color. Now, in many areas, and in combinatorics in particular, we're interested in sort of the quantitative aspects of statements. So you might say, okay, obviously, if you need an infinite set, you're going to need infinite space to start with. How about if I just need to find a red complete graph to do more, everyone joined in the same color in red of size k, or L vertices all joined in blue, then maybe I can just go up to some large finite n. And if I color all the pairs this Kn is, these are always the complete graphs, right? If you take n vertices and all the connections, or k vertices, all the connections, l vertices, all the connections. Maybe if I take a large enough n, even just coloring those n vertices, I can guarantee a structure like that. K vertices all joined in red, or L vertices all joined in blue. And from Ramsey's result, you can use a compactness argument and see this is always finite. I seem to be focusing here on the diagonal case, which is K equals L, but they can be different as well. Erdos and Sekaresh proved a bound on the RKK, which is basically a bit better than 4 to the K. This binomial coefficient is about 4 to the K over root K. But it gives us a very solid and direct upper bound, okay? So you do need to go up to a lot of vertices. Exponential, actually you can prove you need at least exponential, and 4 to the K is enough. We're going to be talking a lot about lower bounds in a minute, so this root 2 to the K, we'll actually see where it comes from in a minute. So if you want to guarantee K vertices all joined in the same color, you will need exponentially many vertices in K, and it seems to be growing exponentially with some base between root 2 and 4, between root 2 to the K and 4 to the K. So yeah, a lot of what we've worked on has been more on upper bounds. That's what I'll be talking about in the second half of the talk, the bit on upper bounds. But I think the lower bounds is probably the part where you are going to see more connections and more use of probability. Now, if you go to a talk and someone says probabilistic aspects of their favorite area, you begin to worry, are they just going to talk about their favorite area and they're just going to pretend it's about probability? And the answer is probably yes, isn't it? So it's probably, I'm just going to talk about Ramsey theory and pretend it's about probability. But you will see the probabilistic tools are engaged in lots of these examples, okay? So what does it mean to prove a lower bound on one of these Ramsey numbers? You need to say for a certain value of n, a certain number of vertices, you can do the coloring with red and blue and not have any of these large subsets that are all colored the same, okay? So if I want to prove, I mean, maybe I could even, I mean, the simplest example is, I don't know, I could just do the simplest example because it kind of shows you what you're doing. There's a famous thing which says if you have 6 vertices, you can guarantee a triangle in one color or the other. And 5 vertices is not enough because you just take a C5 in one color and a C5 in the other color. So if you just have 5 vertices, you cannot guarantee a triangle. And that says you need at least 6 vertices. So this is how you prove that you need at least 6 vertices. So a lower bound of Ramsey number will always be something like that. It will always be an example that shows it is possible to do the coloring and not have this given structure. Okay. So in different cases, sometimes you just drew a picture, right? I just drew a picture on the board. I just drew the coloring. I had 5 vertices to color. I could just do it. Okay. If you're going to do things in the limit, k is going to infinity, all of that, you're obviously not just going to draw it. You need some theory of why it's there. And one of the things I want to try and get across in the first half of the talk here is there's a huge variety of different methods that have been used to get these examples. So I'd say it can be random. It can be random with a little star above it, which will say what it is. It can be random plus deterministic, meaning you do something random, then you come along and do some algorithm on the thing you've produced. It can be you do something deterministic and then you do something random with it. Or it can just be deterministic. So in a way, it's interesting that all 5 of these types, and probably even more, there's some variety within them, have all come up for different Ramsey problems on graphs. So it's sort of a bit strange. You can have such a variety of different approaches, all being, well, at least the best that we know, or the people know, for different problems. So let's have a little quick look at each of them so we can get an idea of what these, also through some examples. So purely random, you might just think, I need to color every edge red or blue. Well, I can just toss a coin, and with probability of half, I color it red, probability of half, I color it blue, and do that independently for every edge. And Erdos, in what must be one of the very first applications of this type of thinking in combinatorics, said, okay, so you have N and K involved here. But what he's saying is if N choose K is not too big, in the sense that when you multiply by this 2 to the 1 minus K choose 2, you're still small. Or in other words, this is going to come from an expected value calculation, this expression here. And if it's less than 1, then you can say there exists a red-blue coloring of Kn with no monochromatic Kk. And that's the same as saying the Ramsey number of K has to be bigger than N. So that's a lower bound on that Ramsey number. So the proof is that you color each edge red or blue independently of probability of half. So it's a really random thing you do. You literally just look for how many monochromatic cliques you make, because you might, it's random. You could do it wrong. It could be terrible. It could have lots of monochromatic cliques. But you just define a random variable for the number you have. You calculate the expected value of that random variable. And if that expected value is less than 1, then that obviously means there has to exist at least one case which gave you 0, right? An expected value is an average. So if the expected value is less than 1, there must be someone who gave you 0. So there exists a coloring with no monochromatic cliques of size k. And if you do the calculation, it's not too difficult to check. This is giving you a lower bound like root 2 to the k on the Ramsey number. It's sort of interesting to think, even if you just think more as a probabilist, you're just going to do this random coloring, probability of half in each color. If you were to take a slightly larger k, what actually happens is this becomes more difficult, right? It's less likely to have this larger clique because you have more things need to happen. And so the expected value will be very small. So it's even easier to avoid if you take k larger. If you take k a bit smaller, then the expected value begins to become large. But you might still think, even though the expected value has become large, there could still exist this really magical coloring that avoids it. And you can be very careful and use the Lovász local lemma, and you can push this argument a tiny bit further, but it really only corresponds to multiplying by a single factor of 2 in terms of the Ramsey number. So using the random graph itself, or this random coloring itself, as our way of thinking or way of working, it looks like it can't go much further than this point. Okay. But as we know, this is quite far from the upper bound, so we're really quite lost about where things should be. What do we mean by random with little star attached to it? So this is another one of our things, and this could mean you're doing some other funny distribution. When your distribution is sort of, independent for every edge, and then that's good for some examples, but maybe in some other cases, you want to change the distribution. And one example of this is the triangle-free process. Now, this came up for people studying R3K. Now, if I say 3 and K, what I'm saying is like in the Ramsey number, you have the 2 different places. The 3 means that in one color, you have to avoid even 3 vertices all joined to each other. You have to avoid even having a triangle. Now, if you try and do like a random process where you're doing the 2 colors equivalently, well, that's a really bad idea. If in one of the colors, you have to avoid a triangle, right? Because they would be everywhere. So instead, what you can do, if you need to avoid triangles in red, you can just add at each step a random edge and do so not with the uniform distribution, but selecting the edge just amongst those that do not create triangles. You know the thing you're avoiding, which is a triangle in red. So you build sort of as big a red graph as you can randomly, keep adding edges, subject to the condition at each step that you never want to create a triangle. Okay. Now, yeah, this was something, I mean, I worked on, it's getting on for 15 years ago now, and you can go quite far with this process. You can sort of analyze how long it should last and all the rest. And it should last roughly this number of steps. Don't worry too much about the numbers, but 1 over 2 root 2 n to 3 over 2 root log n steps. You know roughly how many steps it lasts. And you can say, you know, how big are independent sets in the resulting graph. The independent set is a set without edges. In other words, they're the ones you're going to have to color blue. So this is a bound on how large a clique you find in blue. So it gives some lower bound, the lower bound here, on the Ramsey number R3K. It happens, this is the result as of, you know, our paper, or this is from like 15 years ago now, nearly, or 10, 15 years ago. The upper bound is by Shearer in the 1980s. You can see there's a missing factor of 4, but this is something Marcelo is going to talk about more in his talk. So if you want to hear more recent information about this, then you can see that in Marcelo's talk. Maybe what I'll say briefly about thinking about doing random things with a funny distribution. Of course, you can always have the worry. It's easy enough to say a sensible, oh, I'm going to do a process and I'll include things according to these rules. But by changing the rule, you could change completely the behavior of everything. And you need to be able to understand the structure of what you're creating in order to prove these types of results, right? So what I'd say to maybe a lot of probabilists will know the history more from the probability side. On the probability side in the 70s, you have these people like Kurtz, I think is particularly well known for it. We're kind of looking at how random stochastic processes in certain circumstances ought to follow actually very predictable trajectories. I'm sure there's, you know, there's quite a big literature around all that. But this got adopted by combinatorics at some point in the 90s and called the differential equations method, because often the trajectory you're following is given by solutions to differential equations. So in order to sort of do the, you know, the work of showing you actually behave nicely all the way through a certain process, you work out the trajectory you should be following and then use sort of martingale methods to show that you don't deviate too far from your trajectories as you go along. But I thought I'd just sort of tell you that story rather than give you another 5 slides of calculations or something, because apparently there's already enough slides, and 5 slides of calculations would not be useful. Right, so this is quite exciting. I'm going to give a second example for the funny distribution part. And this is just from last year. So we saw for the diagonal Ramsey number, when you're talking about K and K, the red of size K or the blue of size K, the symmetric problem, then we had this random coloring of Erdos, which we really don't know how to improve, even after, what is that, 80 years? Okay, you could improve by a factor of 2 with a slightly different analysis, but you're using the same random graph. And that's barely any improvement anyway. So what was really interesting is this result for slightly off diagonal. So imagine you have K and L are close to each other. Maybe L is just like 90% of K instead of being equal to K. So what you're looking for in red is just maybe a bit bigger than what you're looking for in blue. It turns out that you can do slightly better than the random colorings. Obviously, if in that case, you wouldn't use a random coloring where the red and blue were equal. You'd use a random coloring where, say, you had slightly more red than blue. But even optimizing over that choice, You could say, well, that's the best you can do with the sort of uniform, independent random coloring. And they managed to do slightly better than that. This is Ma, Shen, and Xi, which gave an exponential improvement on the lower bound for RKL near the diagonal. And so you can see I've done a beautiful picture, and you can obviously tell what the coloring is from the picture. Barely needs any explanation at all. Right, so I've taken a sphere in high dimensions. You put n points randomly on the sphere, and then you say, I'll join in red if the inner product of the 2 points, you could just say positive and negative, right? Let's start with that. Inner product positive, I join in red. Inner product negative, I join in blue. So you join to the half, which is nearest to you in red. Although actually, because they're looking for slightly off-diagonal Ramsey numbers, they're accepting slightly larger cliques in red than blue. This is what this little arrow means. You actually could shift your sort of equator down a little bit. So you'll join in red to anything within a product, at least some minus epsilon for some small epsilon. Okay. Now, this is a plan. I mean, actually, I think Erdos had even discussed similar colorings decades ago, but the analysis isn't so easy. And so it was sort of quite impressive. They managed to push through the analysis and show you could get this improvement. One of the challenges is to understand which dimension you should be working in. I think if the dimension is too large, if you do a very large dimension, I think even like log n cubed, there's a paper on this with Luke and Gabor, isn't there? I'm not remembering anyway. But if you take the dimension quite large, then actually the geometric aspect of it all kind of disappears. And the coloring becomes closer and closer to just being a uniform choice, like it would be in a random graph. In other words, the different edges become more and more independent. If the dimension is too small, if you did this just on like a sphere in, R space here, R3, whatever, then it would be incredibly structured and you'd have very large cliques in red in particular. I mean, maybe in blue as well, but definitely more difficult in blue. Definitely in red. So you want to take some intermediate dimension, and it wasn't really clear that it would be possible to make the right choice. And it turns out it's around log n squared dimensional space, and then you do this sphere, and it turns out they could make the analysis work. But it's a really interesting different twist on doing a random argument, and the interaction with randomness and geometry and everything else. So I find that kind of really very, very different kind of construction and idea, right? I don't know if I fully understand exactly why it works. I think the inner product would be roughly Gaussianly distributed. And if you do an average of a Gaussian in the negative side, I think it's almost going to have a more negative average than the average on the red side. I think this kind of plays a role, but yeah, it's still a bit subtle to me why this exactly works. Right, so we're still doing the story of how all these different types of example are possible. The next one is random plus deterministic. So this is like being a little bit spoilt, and you've got your lovely random object, that's been given to you presumably by a higher power. And even so, you go and complain about it. I mean, it's a little bit ungrateful, isn't it? So this could be, for example, you do that random coloring and you see there's a few little cliques around and you just come along and kill the cliques. I mean, you can do that either by recoloring or by, say, removing a vertex. And this has been used in various cases to slightly improve bounds where you've done something random, but then you're like, I think I'll just change this over here and I'll just change that over there. And it can slightly improve bounds. So for example, in the first Erdos argument, if the expected number of cliques is at most n, or say n to the 0.99 instead of less than 1, you're still okay, because you can then just come along and remove one vertex from each of the cliques. So it's kind of a way to improve your bounds a little bit. And there's also cases, we probably won't go into details with it when we get to the multicolor. We're going to talk about multicolor later, but sometimes you can use structured multi-level examples on which each level you're doing a random process, but you do sort of different copies of it on different levels. So that's definitely a mixture of random plus coming along and doing something deterministic as well. Deterministic plus random. So at first you might think this sounds very similar to random plus deterministic. But in this case, what we're saying is we're going to start with something which is deterministic, maybe coming from an algebraic construction or something similar. And then as it is, it's still not quite right for us, but there's certain ways to apply random processes to that structure that make it work better. And there have been past examples maybe from, maybe Book and Conlon in other contexts have done interesting things with this as well. But maybe the biggest example would be from a few years ago when Matthias and Verstraete showed a new lower bound on R4K. So we talked about that triangle-free process for R3K, where you need to avoid triangles. Here they're in a similar situation. It's just 4 instead of 3. So in red, they have to avoid having 4 vertices all connected in the same color. It's still a very small type of thing to have to avoid. And what they did is, I'm saying, well, really it's deterministic plus random plus random. We have 2 stages of randomness. But what they did is they used a construction coming from projective planes, that's finite geometry, to define a graph which is actually made up as a union of cliques. At first, that sounds terrible. A union of cliques sounds very terrible because cliques are full of cliques in particular. But in such a way that the only K4s, the only complete graphs with 4 vertices you'll find, are the ones that are contained in those cliques. So you don't get any sort of like K4 where I'm going to use one edge of this clique and one edge of that clique and one edge of this clique and one edge of this clique. And they did this all with algebraic considerations. It's in like finite fields, like what, ZQ cubed or something like this. And some algebraic thing about choosing subsets which satisfy some algebraic equation. So it's a really different kind of area to come in and contribute this deterministic object. Once you have that deterministic object, then you do the stages of randomness. Well, one is to say, well, having these giant cliques is clearly terrible. But instead of each maximal clique, each of these giant cliques, you just put in a complete bipartite graph between the 2 sides. So obviously then, that's instead of having a clique, you just have 2 sides in it and you just join the 2 sides. And that looks pretty good. It gets rid of the big cliques in our graph. This would be the red graph, incidentally, right? Or the one avoiding K4s. But it still leaves you with a problem maybe, because having put in a bipartite, there's quite large independent sets. And so what they do is they then have another stage where they randomly sparsify by just zooming into some random subset of the vertices. In between those steps, you do some calculations to bound the size of the independent sets that you find. And then you do a randomly induced subgraph. So it's pretty cool that such a thing is possible. A related problem. So, and I think this isn't so easy probably, but if you just want to use their last step, randomly zooming into a subset, uses something related to containers, graph container theorem. And it kind of means in order to in order to know you're going to win on that last step, you don't need to, or you just need to be able to find, like, as your original, more structured graph, a graph with a certain, this is her definition first, sorry, yeah. We say a graph with density beta is dense on R sets, meaning sets of size R. Basically this just says if it maintains at least a tenth of its density when you zoom into a set of size R, okay? And basically, if you can solve the following problem, I think you get an exponential improvement on the corresponding Ramsey number. So they had these very clever constructions of K4 free graphs, which is after you'd done the algebraic construction, then you change the cliques to random bipartite graphs. And if for any Ks s bigger than 5, you can find a Ks free graph with this number of edges, n to the 2 minus 1 over s, and which stays dense all the way down to sets of size root n, then you can already get an exponential improvement on that Ramsey number as well. So in particular, say S is 5, can you find a K5 free graph? This would be like with n to the 1.8 edges, and which maintains the same density up to a constant down to sets of size root n. Now, if you can do that, you can improve that Ramsey number by, I said exponential factor, right? I mean a polynomial factor, by a polynomial factor, because these Ramsey numbers are just polynomial. Right, so it might seem strange to people who are not in the area, who haven't thought about this stuff, but you might, it's nice you think about other areas and you just assume people are kind of somewhat competent in the things they're doing, right? And you must be thinking, well, people who do graph theory all their life, they know if a graph exists with like some really obvious properties. We don't. Like constructing graphs with certain properties like this, if it's random, we can do random and it's okay. If it's algebraic, then maybe by magic there's some algebraic construction. But if they may be quite reasonable, this should exist. But if you don't have the way, if you don't have some, so, you know, if anyone can think of a clever way to construct graphs like this, it'd be great to know. Maybe it's more likely to be algebraic, but who knows? Maybe there's some crazy probability distribution you can put on by some process and find these things. And I think that would improve, give a polynomial improvement for the lower bound on RSK. Okay, now, finally, I put deterministic on the list because it really does occur. Probably for a probability group, I don't need to talk too much about deterministic things. You're not fans, are you? You're not fans of deterministic things. There's certain other types of Ramsey problem where you need to find other graphs colored in red and blue, where you literally just do constructions which are blue cliques and red bipartite or that type of thing. And it's kind of believed that maybe for just the diagonal Ramsey numbers, you could get constructions by doing quadratic residues modulo P, and it works in Z17 for K4s. But that seems to be difficult to analyze as well. And in fact, on the deterministic question, it's open even to prove any exponential lower bound on R of K by a completely constructive method. In other words, any talk of lower bounds on Ramsey numbers, it basically has probabilistic aspects, doesn't it? Because constructively, we can't even do exponential. So, you know, without you, I'm nothing or something, I should say to the probability, you know, without probability, we're nothing. That's all we can do. So now it's a natural moment if you have questions or if there's any comments or questions, we can talk about those now. Afterwards, I have something on multicolor case, multicolor Ramsey numbers, but if anyone has any
If anyone
comments
has
or
any
questions,
questions, I don't know if you can unmute yourself or if you need to raise the hand. I apologize for all the administrative issues. This is our first time doing this. If no one does, I will jump through. I guess, and this is an ignoramus's opinion, but a lot of this seems like magic. In the sense where you need, like, is there sort of any a priori way to say, oh, this geometric construction, this random construction, I can sort of understand, but as you said, this is the kind of things that I find to be simple. But like,
Yeah.
what distinguishes? Why is K4 the thing we can do and you can't do it for K5? What is it like? Is there something fundamental in the algebra or in the geometry? Is it if we move from Euclidean space to an LP ball or something? Like, there's so many sort of free parameters here that one would imagine could change and maybe think, but it just, I'm certain, as you said, people are competent, but
I think some of these things, when you don't know the other cases, you do begin to feel it's a bit like magic. I mean, there's something similar in extremal graph theory with how many edges can you have if you avoid like a C4 or C6, like certain subgraphs. And for C4 and C6 and C10, there are algebraic constructions which do match the best upper bound we know, but only for C4 and C6 and C10. So I guess I'm just giving another example where it seems like very particular constructions work in certain cases.
And there are structural descriptions of such things that are sort of underlying it, the fact that the C4 free graph has certain properties.
If you say to me, like, is there an answer? Is there an answer of why it doesn't exist for C8? I don't know. I don't think anyone has a good answer for that. I mean, it could be it does exist and we just can't see it, or it could be that it doesn't exist and then it's just a very bizarre to even try to think how you'd begin to answer why. But I mean, yeah, I feel like we do feel a bit clueless, particularly, yeah, and I think probably people have thought about trying to do something similar algebraic for K5 now. Obviously, it'd be a very natural next thing to think about, but maybe you just need a
question by Andre Strakar. I don't know if you saw it. Asking, are the funny distributions limited to those that you presented?
Are the
quote unquote funny distributions limited to those that you presented?
Right. Let's see. So in a way, what Marcelo is going to talk about in his talk is kind of a different funny distribution. So you can wait and you can see that one for sure. I'm trying to think if there's other completely different things. I mean, yeah, obviously, like the triangle free is just one example. Obviously, you can do free of any, K4 or K or H or so that's kind of a class of things. Yeah, and I'm not immediately thinking of other ones. There's other ones involving spheres in Ramsey-Turan theory that you use spheres again. But yeah, maybe Marcelo can think and he can answer that for me at some point if he could think of any other crazy distributions that have been used. Right. So shall I wander on for a bit more then?
Please, and we'll ask, and if you have any more questions, we'll do another one of these at the end.
Okay, yep. Yeah, so now for something completely different. I mean, completely different, not really completely different. It's not so different. It's only different in the sense that, well, we're now going to allow there to be more than two colors, right? So you could have red and green and blue, or red and blue and green, whatever. Because we're doing red and blue, we could have red and blue and green. And sorry, this is, although we're going to start with a recap of the two color case. So the results here are now looking at the upper bound, right? So the upper bound is what's a large enough number that I can guarantee the structure. Sorry, this slide is very full, but so what we'd said before was this 4 to the k, right? It was an upper bound that you can always get. And then over the decades, there was some progress on improving this upper bound. Thomason in the 80s got an improvement of roughly root k. Conlon managed to push quite a lot further and getting almost e to the minus log k squared. He just had to divide by log k. And Saar, well, this came out, I think, just about in the pandemic, managed to get the log k squared. And this was, yeah, the limit of a certain method they were using, which was a method not of randomness, but of quasi-randomness. So here you can't say, I'm going to use randomness, because when you're proving an upper bound, you can think of it as your enemy. I'll say your enemy, your opponent or your enemy gives you a coloring, right? You are given a coloring. If you want to prove that this many vertices is enough to always find a monochromatic clique of one of the two colors, you don't get to make up the coloring anymore. Your enemy makes up the coloring, and you have to say, I can find one of the cliques, a red or blue clique in here. And so in a way, it's almost like inspired by the fact that the random was a good lower bound. You can look at the coloring your enemy has given you and say, does this kind of look random? And that's the property of quasi-randomness. And if it looks kind of random from the points of view of degrees and co-degrees and things, then the theory of quasi-randomness lets you show that various other random-like properties will hold. And that can actually be useful for then going on to find cliques. But as we say, the limit of that method wasn't going to give you an exponential improvement on the upper bound. And then with Marcelo and with Rob Morris and Julian Sahasrabudhe a few years ago, we did manage to do an approach which got the exponential improvement. And that was slightly improved, or improved numerically, and slightly different. Well, they had some variation on the technique by a group the year after to 3.8 to the k. I was just, yeah, that would clear my drawing. Sorry. But I'm not going to dwell much on the two-color case because I sort of want to get on to, well, we'll say about the ideas, and then I can mention the multicolor thing and what happens there. So if your task is to find, the Edel-Sekaresh argument to find a clique is you can do this neighborhood chasing. You just take a vertex and say, well, it either has more neighbors in red or blue. If it has more in red, I'll just take V1 and just take its red neighborhood. And then if pick a vertex, V2 has more neighbors in blue, I just pick V2 and take its blue neighborhood. And if you keep zooming in and doing this, after you get to 2k plus 1 vertices, you realize you must have used the same color k times. And if you inspect those k vertices, you actually find a complete graph on k vertices. And this drawing below is saying almost equivalent. You could actually, at the moment you choose a vertex and restrict the neighborhood, you could sort of put that vertex in A if it's red, and it will form a clique with the other red vertices. And it will be every edge from A, if you restrict X each time to either be a red neighborhood or blue neighborhood, you can maintain this at X, which joins just in one color in red to A and in blue to B. And the reason you have to get 4 to the k for this type of argument is that the set X goes down by a factor of 2, whether you do a red step or a blue step, even though in the end, you need to do k steps just in one or the other. You end up having to do 2k steps because you can't control which type of step you do in each case. So the intuition you'd think is, why not just do red steps? Why not just go down, keep doing red steps and just go down by a factor of 2 each time? If you really could do this, if you managed to do this for even, a constant times k number of steps, you will make an exponential improvement on the upper bound. So that was something we had in mind. It's all pretty similar for multicolor. There, the Edel-Sekaresh bound gives something like R to the RK instead of 4 to the k. I won't say much about lower bounds. They are actually interesting, and they do have elements of combining methods, like Conlon and Ferber as well are combining an algebraic thing coming from Z2 to the N with a random coloring, so using those two things together. And actually, there's some news from last week and this week improving on Sarwin's bound just a little, which is basically using the random spheres argument combined with some of the ideas of Sarwin. In terms of the upper bound, which I'll go back to for time reasons, I should mention more on the other things. So we had our first paper, and then naturally, to get any further, we needed to double the number of authors. So with Ballister, Bolabash, Campos, Hurley, Morris, Sahasrabudhe, and Tiber, we got the exponential improvement on also the multicolor Ramsey numbers. The first proof really just worked for 2 colors, but now this works for any number of colors. If you're doing R colors, you can get an exponential win in terms of K. So for 3 colors, if we just want to talk about that, it was 27 to the K, and now it's 27 to the K times e to the minus delta K for some tiny delta. So again, the equivalent here to win an exponential factor would be to find this book-like structure. We call it a book for some reason, where this here is a complete graph on the left. It's all joined in red to each other. Yeah. And all red between the left and the right. Okay. Here you'd usually be losing a factor of 3 each time if we're doing 3 colors. So you'd be happy if you do this for t steps, and the A is around 3 to the minus t times A. Okay. Now, we end up doing it via a thing which seems completely unrelated. Here's a weird lemma about a random variable. If a random variable has positive expected value, well, you wouldn't expect it to always be less than -1, right? It can't always be less than -1 if it's positive expected value. So either we have a 10th probability of being at least -1, or if you're really pushing it all to less than -1, the little bit that is positive, in some sense, should be very positive. You don't know where it's going to put that positive weight, though. It could put it at a small positive number, or it could put it at a very big positive number. If it puts it very big, you might not need so much, right? But anyway, you can do this lemma. Either at least 10th is at least -1, or for some lambda, you have probability at least 1 over 2 lambda squared of being at least lambda. This is not at all revolutionary. Probabilists will look at this and be like, oh dear, this is just like a simple integration, and why is he telling us about this? But imagine if you didn't have the first property, then you have at least 90% chance to be less than -1. Obviously, you have most 10% chance of being positive at all. So the expected value of the negative part is less than minus 0.9. The expected value you're getting from this little part here is at most 0.1. And we want to show that you have the other property for some lambda, the probability x bigger than lambda is at least this value. Well, if this doesn't hold as well, then you can just bound how much contribution to the expected value you're getting from there, and you can get a contradiction. Okay. This lemma, I'm not saying it's an interesting lemma. I'm just saying it is a lemma. Okay. But what we then do is we want to do something which is kind of like a multi-dimensional version of it. But let's first introduce it just with 1 dimension. And I'm going to do it in the language of a dating app because people find this funny. So you have the users of a dating app. You have a personality test, and you want to match people who are similar, maybe. And you'd want to know there's lots of pairs that the pairs of people are similar. Well, if you sum all the inner products of your personality test maps you into RD. If you sum them over all pairs, this is non-negative by, well, algebra. And so if you think of selecting 2 people at random, the expected inner product is non-negative. And so applying that last lemma, either you get a decent proportion that are at least, I think that should be -1 actually, but at least -1, or there's some select group of pairs which are getting a much better match. And the key lemma we do, the geometric lemma, is basically you have several functions instead of just one. Maybe you have a personality test and a life goals test and an interests test, and you want to coordinate on all of them. So the event E is that you have inner product at least -1 in all three. And this will tell us either you have a decent proportion of having a reasonable correlation in all three, or in one of them, you can expect something much better. You can be a bigger than lambda for some lambda. And it's a very similar proof to the other one. It just involves using a funny function with cosh and doing everything in a few dimensions. So I can see we're kind of at the end in terms of time. Maybe I'll just very quickly say, what's the relation between this multicolor Ramsey number and the funny geometric thing? Well, if you're doing this process of trying to build a structure like a book, you don't know which color is going to work very well. And now we have 3 colors going on. So you need to actually, this is going to be, this is going to be a clique, this is going to be red, and this is going to be a clique. I did the sides wrong when I labeled it, no. This is going to be a clique, this is going to be red, and this is going to be a clique. Oh, sorry, that's blue, and this is going to be purple. So actually, one of the most important things, you can obviously imagine if I take a vertex, I can add it to A and restrict this X to just the red neighborhood, and that's a valid step. I will still have the same structure. I want to do this when I keep about, I have to restrict the red neighborhood in A. So, oh no, sorry, these bits are, I'm messing up the description. Yeah, these bits you don't yet have. I'm saying all the wrong words. Let me see. Yeah, no, sorry. The bit on the right is going to be the yeah. It's all about, as you go through the argument, maintaining a density, because you start with densities maybe around a third, because you have a third of each color. And you want to maintain densities between the two sides as you go through the argument. And if you imagine, if I'm going to do a step where I restrict to a red neighborhood, you might wonder, how does this change the density from some other guy to here? Well, that's really like the relation between their two red neighborhoods. And then if you represent each of them by their red neighborhoods in sort of RD, it's really like a correlation or an inner product, right? Because you can do maybe the weighted neighborhood. So it's really like how well they work together from this argument is to do with their inner product. And what you'd really like to find is a good number of pairs in here which work well for all 3 inner product problems. And that's exactly what the geometric lemma can give you. If you find a good number of pairs which are good for all 3 types of step, then actually you know that at least a third of these have to have the same color within the left. Because a priori, the coloring in the left and the coloring across could be completely unrelated, or your enemy could be, producing them together in some clever way. But getting some number of pairs that work well for all 3 bipartite graphs kind of gives you a way you can take some of them, but these work well together and they're joined together in red, and then you can do the appropriate step. But I can't go into any more details, of course, because of the time. I can just say, in the other case, where instead it was giving you this lambda and you had something much better in one color, it corresponds to something we call a density boost step. And then we restrict on both sides and increase a density in the color we like. But anyway, it's probably best to stop there and see if there are any other questions about this part or the other part, or whatever you like.
Simon, thank you very much. That was a lovely talk. I don't know if I'll clap for everybody because I don't know how to unmute everybody at this point. But if there's any questions, please either unmute and raise your hand or ask them in the chat. And if not, I will use host privilege to ask a quick, slightly technical question, just because the large deviationist in me can't help myself. Because those two, that lemma seems to be an anti-concentration. It's this. It seems that you're saying that these things actually have to vary. If the mean is 0, what you're getting is actually anti-concentration. It's not actually near 0. You have to have mass here or here. Is that in the other case? Is that a correct way of reading it, or?
Right, although I think if it was all near 0, I think we just take that as a win for it all being at least
So yeah, that's the case. That's the first case.
Different. Yeah, it's a slightly different. I think we just our big fear is somehow it could be that the pairs that are good for one of the functions are bad, or in that case, it's points, isn't it? Good for one of the functions, or the pairs are good for one of the functions and not good for the other is not good for the other function, and they kind of all because I guess your fear when you go to a picture like this is the ones that are colored red in the left-hand side, they behave badly with respect to the red bipartite graph, and the ones that are colored blue behave badly towards the blue bipartite graph. So our nightmare is that somehow every pair manages to behave badly exactly to the one you don't want it to. So we kind of want there to be some that are behaving well towards all of them. In terms of that geometric lemma, the proofs actually, your first thing you do is actually show that in the same way as I said, you can do the expected value and it's non-negative, right? You can actually do all moments. So all moments and cross moments of these things with the three different functions are all non-negative. So that's kind of a lot of information. And then we use that together with some crazy function that helps you give those estimates. But I don't know if there's a correct name for that type of result. Do you know a name, Marcelo? What's a name for a result like that? I don't know.
I don't know. Yeah, it's kind of like I don't know if maybe someone in probability knows this phenomena, but I don't really. I never saw it before, like these kinds of things where you need to show like a random variable, like two random variables are both positive. There's some mass on the positive quadrant.
Mm-hmm. And did you come up with another different example of some funny distributions that people have used in Ramsey theory?
Yeah. So one thing is this these lower bounds for multicolor, they are like also kind of like, especially the solving ones, they kind of have funny distribution. And so he like does a blow up and then mixes in like a blow up of GNP and mixes in like permutations of other random things. So it's kind of funny. And there is also this, it's not exactly Ramsey theory, but this Boris book paper that they showed the graph is given by the zeros of a random polynomial. It's like a two-variable polynomial, and then you take the zeros of this random two-variable polynomial, and this gives you a graph, and this graph is good for extremal numbers, like the problem Simon said.
Yeah. Pretty cool.
Thank you very much. I think we'll take a very quick break, mostly because I have to run to the restroom, and we'll have Marcelo set up and return shortly.
Thank you. Cheers.
Okay, so let's continue. We are going to start the second part of the presentation. Please, Marcelo.
Hey, hello. Thank you for inviting me. And thanks, thank you, Simon, for the very nice presentation. First half of the talk. So, can you see my slides? No.
Yes, we can see.
Okay. Start presenting here. Okay. So the second part of the talk, I'll focus on like two specific problems in Ramsey theory. So like the first half of my talk will be about one of them, and the second about the other. And I'll do like a more like a kind of a detailed description of what is that like about them, as much detail as I can go on in like half an hour. And so the idea here is I'll be talking about this off-diagonal Ramsey number R3K that Simon like mentioned a bit in his talk. So he said that he mentioned that this triangle-free process, and I'll just do a slight change of notation here. So instead of colors, I'll talk about graphs because I'm just taking the edges of the graph as the blue edges of the coloring and the non-edges of the graph as the red edges of the coloring. And in this case, what we're interested in is this quantity alpha G, which is the independence number. So it's the size of the largest set of vertices which don't have any edges between them. And so another way to phrase the Ramsey number R3K is the minimum size such that any graph with independence number at most k always contains a triangle. And so okay, so this is the problem we're interested in, and these are the Ramsey numbers we know the most about. So so I'll be able to go on about quite a few results that we have about this and get to some very very nice situation where the bounds are very close. So Erdős Sakaras already in 35 they show that these numbers are most k squared, and the idea here is like basically just a greedy algorithm. So you take some vertex v1 and you look at the neighborhood, and if there's any edge inside the neighborhood, then you have a triangle. So the neighborhood must always be an independent set, and therefore we know that it has the most k vertices. But then we can take a second vertex v2 that is not in this neighborhood and look at its neighborhood and ask the same question, and we are always deleting the neighborhood of these vertices. So since every time we take a vertex, we delete at most k neighbors of it, if we go for like k squared steps, we're gonna find a set of k vertices which are all independent, right? There is no edge between v1 and v2 and so on. And if there is ever a vertex that has neighborhood of size bigger than k, we take the neighborhood as the independent set. And the first example of probabilistic method of this probability application to R3K that I would like to talk about is actually in upper bounds now. So is this very nice work of Aitai, Komler, and Shearer that improves this classical result of Erdős Sakaras by this factor of log k. And the idea is to basically do a very similar process, but instead of just doing a greedy process, you are going to do a random greedy process. So instead of just choosing an arbitrary vertex to start with, you're just going to choose a random vertex to start with, v1, and you're going to again delete its neighbors. And you can always assume that it has the most k neighbors again, because otherwise you take the neighborhood as the independent set. But you're gonna track how the number of edges of this graph evolves. And the crucial thing is that in the beginning, okay, you might be excluding k vertices, but as the number of vertices in the graph decreases, the size of the average degree also decreases. So you're gonna be excluding much less than k as the process goes on. And so you can you can drive this process on for longer. And this is basically just to track a random process, like to show this works. And in the end, they are taking vi at random, in the vertex set of the graph minus the neighborhood of the first I-1 vertices. And then they show that the expectation of the set I that you make this way, just V1 up to some number, is going to be at least log of the max degree over the max degree times V of G. And that max degree will be like K. So we get like an extra log K factor here. And this, if you translate this into Ramsey land, this means you get a log K in the bottom of your bound. And there are actually other proofs of this and other proofs using probability. For instance, there's some very nice proofs using the hardcore model, which is this model where you're just choosing, like, for instance, a uniformly random independent set in your graph, and you show that the expected size of this independent set is large. But yeah, it does come in also in the upper bounds, as we can see here. But now I want to talk a bit about lower bounds as well. Because for lower bounds, one of the first applications of this probabilistic method was Erdős in the 50s, and he showed this bound of R3K is at least K over log K to the 3/2. And it's an example of this what Simon said was random plus deterministic. So it's basically like this alteration. So you take a random graph, maybe it has some triangles, but if it has less triangles than there are vertices, you can just delete one triangle for every vertex and get a triangle-free graph. And since it was a random, and since you're just deleting vertices, you can't have increased the size of your independent set. So if your independent set has size at most K in the beginning, it still has size at most K after you delete vertices. So the basic idea here is just this simple vertex deletion argument, and gives this K over log K to the 3/2. But then this turns out to be somewhat inefficient, because a much more efficient way of deleting triangles is, instead of deleting one vertex from each triangle, is that you delete an edge from each triangle. And Erdős in 61 showed that you could actually just, as long as your number of triangles was much smaller than your number of edges, you could just delete one edge from each triangle, and you wouldn't be deleting too many edges from your graph. And then this is much more challenging to show it works, because now if you're deleting edges, it could be that you're in something that was like not independent before suddenly becomes independent if you delete edges from one side of it. So the main challenge is to try to show that this edge deletion bit won't make the size of your largest independent set larger. But Erdős did manage to show that, and the idea is that, like, not only sets of size K will have one edge inside of them, they'll have a lot of edges. So it will be very unlikely that the edges you delete, which are a small proportion of all the edges in your graph, are exactly all the edges inside your possible independent set. Okay, so this is this deletion threshold, and now one would like to somehow do better than that, and was a breakthrough by Kim like 30 years later that managed to show that you could actually get this a log K better. And maybe you don't remember the upper bound, but the upper bound was of the form K squared over log K as well. So this is the first time we knew like a family of Ramsey numbers up to a constant factor. So this is showing that R3K is up to a constant factor, just K squared over log K. And this paper by Kim is very nice because it uses like a lot of cleverness. And it's kind of funny that the same technique that is used for the upper bound in this problem is also used for the lower bound, because it's also going to be a random greedy process. But the random greedy process is acting on a different place, right? So in the upper bound, you're given a graph and you'd like to find a large independent set or a triangle inside of it. And in the lower bound, you'd like to construct a graph that doesn't contain a triangle and doesn't contain a large dependent set. And the way he constructs this graph is by sprinkling random batches of edges. So kind of like a random greedy type of approach, because he's choosing like uniformly random these edges and then sprinkling in. and then he's deleting the triangles for as this process goes on, but he also does all their manipulations. So deletes triangles by, sometimes he deletes edges, sometimes he adds edges and adds vertices. So, and the key things that it's kind of hard to track these types of processes. So he does like various manipulations to make the process more regular and to make it something he can track to the end, this type of process. And you might wonder, okay, is all of these manipulations necessary? Can't you just track a random process? And this is what Balabach and Erdős asked in the 90s. And this is the triangle-free process that Simon was talking about, which is so I guess what I'm talking about here is like various examples of funny distributions, as Simon said, like this Kim distribution is like kind of a funny example, and then this triangle process as well. And the idea is that you start with an empty graph, and you start with some set O0 of open edges. So I'll call this set OI always the set of current open edges, and the sets the edges that are not open or closed. So as the process goes on, it's going to close edges, and the edges you're going to be able to take are always only the open ones. So you select a uniformly random some edge from the set of open edges, and you add it to your graph, and now you're going to update your set of open edges. And the edges that are open is just the edges that don't form a triangle, wouldn't form a triangle if you added it to your graph. So the sets of edges that are closed is exactly the edges that form a triangle. So like if you have something like this, then this edge here is closed. And then the key thing is that if you're doing a process like this, you never form a triangle just by definition. And the hard thing about this is to track this process and show that it has like it attains some good density, and also that somehow it produces a graph which is like similar to the random graph. Because somehow one pseudo conjecture that is around is that the graph that minimizes the independence number, the triangle-free graph that minimizes the independence number for a certain density, is kind of always the triangle-free graph. It's always the like a random type of graph. So we think the random graph is kind of like a minimizer for the independence number if you fix the density. So like the best way to get smaller independence numbers just to try to increase the density while keeping similar to the random graph somehow. And so the hope here would be to show the process runs for long enough that you can actually get your independent sets to be small, and then this is the whole point here. And this is what Bowman showed in 2008. So he managed to track this triangle-free process up to like for say 1% of its running time, or for 10% of its running time, so like some constant proportion of its running time, and show that this implies that R3K is at least constant K squared over log K. And he uses this technique that Simon briefly mentioned, this differential equations method that we have in, it's like a technique in like combinatorial random processes, which is derives its name from like the fact that like these random variables follow some some kind of differential equations in general, like, and you track a bunch of random variables together. And then Bowman and Kivash and Fispontiveros, Simon and Morris showed that R3K is bigger than K squared over 4 log K. So this is just a gap of a factor of 4 away from the upper bound, as Simon mentioned. And the way they did this is by tracking this triangle-free process until the end, the end of its running time. And this is very, very challenging, as it turns out, because there are like, it's kind of very hard to show the process always keeps on track, especially as you get to the later stages. There is like a lot of ways it could go go off track. So they need to track quite a bit about how the structure of this graph is evolving. And so this paper is like they're like 100 pages, and it's very challenging, and I think it's like very beautiful math as well. So especially because I feel like this is like the prettiest way to generate these triangle tree graphs is just, okay, you have like this very nice, very simple to define random process, and you're gonna generate a random graph using that. And it feels very natural and like an interesting object to study. And then Fontiveros, Griffiths, and Morris made the very nice conjecture that actually this is the tight thing. So like this very natural object, and this is kind of, you could think is like the most random triangle way to generate a triangle free graph. This gives us a tight bound on the Ramsey numbers. So there's a factor of 4 missing in the upper bound. And just to describe a bit more about where this number exactly comes from, this 1/4, which they prove, is that we say, okay, an edge is open if when you put it in the graph, it's still triangle free. And to see a bit about how what is the final density of this process, we need to think a bit about what is the probability an edge is open. And we're going to assume this triangle free process type thing generates a graph that is very similar to like a fully random graph. So like each edge is included independently with probability p, say. And so let's say it has density p, your current graph has density p, and then the probability an edge is open, maybe it should be like 1 minus p squared to the n, because it would be the probability. So the probability that include each cherry like this on top of this edge is p squared. So the probability you don't include is 1 minus p squared. And then you have to do it independently. Well, supposedly independently, though it's not really independent, but let's assume for a second it's independent. You would do it for n minus 1, actually, different vertices. So the probability would be kind of similar to 1 minus p squared to the power n. If such a graph was very similar to like every edge being chosen independently. And the challenge is exactly to show this is the actual real behavior. And they show this is the real behavior. Like I'm not lying to you when I say this is similar. This is actually true, but it's very hard to show. And if this is true, then the number of open edges should be similar to e to the minus p squared n, which is the probability an edge is open, times n choose 2, which is the number of open edges. And maybe you should basically end the process whenever this quantity here, like the number of open edges, is much smaller than the number of edges you already have in your graph. Because even if you add now all the open edges to your graph, all these edges you add to your graph, you wouldn't really make a difference about your density. You only increase your density by a factor of 1 plus epsilon. So we don't really care about like such a tiny increase. So maybe we end the process when this happens. And if you calculate what p is in this case, you get that p should be like square root of log n over 2n, which turns out to be actually the final density of the triangle free process. So this is the heuristic to give you what the final density of the triangle free process should be. It's like you calculate the number of open edges. It's whenever this is smaller than your current density, basically it means it ends. And well, the other thing they show to finish the proof is basically that the independence number of the triangle process, the largest independence set in the triangle process, is very similar to the largest independence set in just a binomial random graph with the same random graph with the same density. So if you just put every edge randomly with probability p, or if you run the triangle free process up to density p, these two things have the same independence number, which is also very hard to show, but they do show it's true. And one thing that is kind of interesting about this picture is that while SP increases, the independence number decreases. And if the independence number decreases, you're getting a better lower bound. Like if your independence number is smaller as a function of n, it means you're getting a better lower bound on your Ramsey number. So like these things are kind of confusing, but it does go this way. So SP increases, the independence number decreases. So if you have more edges, your independence sets are smaller, and then you have and you're proving better lower bounds on your dependence number. So if somehow we could keep this property star, so this property that your independence number looks like the independence number of a random graph with the same density, but get our random triangle-free graph to be denser, then we would be very happy. And turns out this is the heuristic to refute the fact that the triangle-free process does give the optimal answer for this R3K problem. So myself, together with Jensen, Michelin, Sarstabuda, we showed that actually we could improve this constant from 1/4 to 1/3. And the idea to improve it is exactly to take a graph that is somehow slightly denser than the triangle-free process in the end of the triangle-free process, but it still like has enough randomness that its independence number looks like the independence number of G and P. So it's still like random-like enough to get such a result. And we did conjecture that actually the optimal constant is a half instead of a third. And then the main idea to get this slightly denser triangle-free graph first is one very good way to generate triangle-free graphs that are very dense but don't necessarily have small independence number is to take blowups. So a blowup is just, imagine like I have for instance, a C5 here. And if I'm doing a blowup, is just that I'm turning each vertex here into, say, a blob of our vertices. And then I'm connecting all these R vertices by a complete bipartite graph. So this is our blowup of this graph. And the idea is that I'm going to take a random graph where I connect every pair of vertices with probability P. And P will be this quantity, doesn't really matter, but let's say it's this quantity. And then I'm going to blow it up by a factor of R. Yeah, so then every vertex of this graph will turn into R vertices of the next graph. And this procedure turns out to be terrible for independence number, because if you have an independence set in this graph, when you blow it up by a factor of R, it just gets a factor of R bigger. But it's very good for avoiding triangles, as we're going to see in the next slide. So now, if I compute the probability an edge is open, but in this model where your graph is a blow-up of a random graph, of a p-random random graph, now the probability an edge is open will be the following. I take two vertices, and now I need to see if they have some triangle. They would form a triangle with someone, this pair of vertices. And the point is that now, instead of having to check n vertices, I only have to check n over r blobs, right? Because I know that I'm only connected to this vertex if I'm also connected to all the r vertices here. So I have to check like less things instead of checking n. I only need to check n over r. And the big win here is now that your probability of being open, well, probability of each blob closing this edge is going to be p squared. So the probability of being open would be 1 minus p squared to the number of blobs, which is n over r. So you're winning the factor of r here in the exponent, which will be very convenient because you can take r to be quite large, actually. You could take it to be much bigger than log n, and then this probability, it's almost 1. It's like 1 minus little 1. And then, okay, then there's still a problem, right? Because if I'm doing this procedure, as I said, I still have very large dependent sets. So I have to have some way of killing them. And the way we do it is by running a triangle-free process after we have this blow-up. So you take the blow-up, and now on top of that, we're gonna run this triangle-free process, and we have this seed. So G0 is this blow-up, and O0, like the set of initial open edges, will be the edges with our open with respect to the seed, which is this blow-up. But it's almost everything is open, so this seems like a good situation. And it turns out that, okay, I told you before that tracking the triangle-free process to the end is very hard, right? Like I told you that it's a very challenging thing. It takes 100 pages. So we don't actually track the triangle-free process. We take like a approach that is a bit more similar to Kim in a way, which is that we do a modification of the triangle-free process that turns out to be very simple and makes a huge difference, which is the following. Sometimes we're going to do something very counterintuitive. So if we have two edges, E and E prime, one of the main issues in triangle-free process is that the probability after some amount of running the process, maybe the probability E gets closed start getting kind of different from the probability E prime gets closed. So probability E gets closed. Is different from probability E prime gets closed. So, and one of the main issues in the triangle process is like in tracking the triangle process is showing these probabilities don't actually get too far apart. They are always kind of similar. But then what we do instead is just sometimes, so if your probabilities are different, then I'm just gonna close the edge E by using some independent random variable just to make sure these two probabilities are always equal. So I'm going to close more edges than is necessary, but this is going to regularize my process because I'm going to make sure that the probability every edge is getting closed is the same. So like it's kind of restricting my process, making it harder to find like a large graph which is triangle free, but this is worth it because it makes everything much easier to track. So the main modification is exactly this. It's just closing edges arbitrarily so that so I'm saying that I'm gonna close this edge even if there is no triangle on top of it. It gets closed by magic. And yeah, and this makes the process much easier to track, though it's like a bit less natural, right? Like, no, there's this regularization step, and a trick that Alan, Kim, and Spencer used in a paper about designs, and turns out it's very useful in various circumstances when you want to track a random process to construct an object in combinatorics. And you actually don't care really that you're following the correct random process. So you just like throw in this regularization step just to make sure the random process is easier to track. Okay. And we get a third with that. And then the very nice thing that happened at the end of last year, there was this amazing paper by Hefty, Horn, King, and Fender showing the half of our conjecture about the correct value of R3K, which is that R3K is at least K squared over 2 log K. So it's within a factor of 2 of the upper bound. And it kind of says that if a random graph is kind of the minimizer for the independence number in a certain density, if you don't have triangles or other dense structures, then this result would be tight. So this is kind of getting to that point. And the main idea there is that actually there is no reason to run this triangle-free process at all. The correct thing is just instead of using a blow-up and a triangle-free process, is just to use 2 blow-ups on top of each other. So they take 2 blow-ups of G and P, and they permute the vertex set so that the parts, the blobs in one of the blowups don't have anything to do with the blobs in the other blowup. And you can see here my amazing artistic skills to trying to draw this, but it's just like the red thing is one of the blowups and the blue thing is the other blowup. And the important thing is that the blobs don't have anything to do with each other. So they just permute the vertex set uniformly at random to make sure that the way they fit together it doesn't make any reference to the structure of the blobs. And the very nice thing now is that one blowup is gonna kill the structured independent sets in the other blowup. And you still have this property that I showed you before, that a blowup will close very few edges. So so most edges will be open, and this is like a very nice property about using these two blowups. And then there is some information about independent sets that I drew here. So there's this this point that I'm making, that I'm drawing two graphs here. This graph, the y-axis is the number of independent sets of a given size, and the x-axis is the size of these independent sets. So you see the size of so the last place where we have some independent set of a given size is this 2 log Pn over P. So it's the last place where this graph is bigger than 0. And then, but the place where the number of independent sets is maximized is at exactly the halfway in this graph. Halfway in this graph is this log Pn over P. So exactly a factor of 2 away from this. And then this is the graph for G and P. And then when you look at the graph for the blowup, what happens is that you have basically everything looks normal up to halfway point, and then from halfway point onwards, the best way to make an independent set will be to take an independent set that is on this peak here for G and P and just blow up the vertices of it. So just take like multiple copies of each vertex for an independent set that is on the peak there. And so it turns out that these are what we call structured independent sets. And the idea is to use that we don't want to have this structured independent set. So we want to show that when you take the union of the two blowups, your graph looks like the graph in G and P. So like you still look like the number of independent sets, like your independent sets still look like G and P basically. So you want to kill the structured independent sets. And the point is that each blowup kills the structured independent set in the other blowup, because it doesn't make any reference to the other partitions. The two partitions are completely independent from each other. So they manage to like they don't see the fact that these independent sets that are after halfway point here are actually structured, because they are not structured with respect to blowups, only one of them. And this is what I wanted to say about R2K. And then I'm gonna do the same thing as Simon. I'm gonna change topics. So this is a very good place to have questions, if there are any, about anything I said so far. If there is any question in the chat, you can read.
Is there any connection to percolation?
This is a good question, actually. I'm not sure, because I feel like we're working in a regime that is like kind of above the place where percolation type things show up in random graphs. So like, for instance, could I ask at some point how, when the random graph becomes connected, and these kinds of questions obviously related to percolation. But I'm not sure if these thresholds we are looking at, there is some kind of percolation phenomenon happening as well, or if it's like a purely combinatorial phenomenon.
And the second question was if this can be used in practical empirical settings.
I'm not sure. Like, I think no one has tried to program this, but I don't think it's I don't think the error bounds are that bad. So I think in principle, I think it would be kind of interesting to try to just like program this process like of like sticking two blowups on top of each other for small examples and see if you can like get anything resembling the upper bounds we have for small Ramsey numbers. So like if there is like any evidence to the conjecture that half is actually optimal or not, or if there is some way of getting evidence for that using some small numbers, I'll be interested in that. Okay, so now I'm gonna change topics if there are no more questions. And I'm gonna talk about this other problem in Ramsey theory. So it's a bit of a maybe, yeah, might seem a bit weird at first, but I promise you there will be like a lot of connections to probability, especially in the methods we use, and especially to like large deviation estimates and things like that. So the idea here is we're interested now in Ramsey numbers again, but now we're not interested only in cliques, we're interested in some arbitrary graph H. And we're not interested in finding it as a normal subgraph, we're interested in finding it as induced subgraph. And I'm going to say a bit more about that in a bit. So the induced Ramsey number of H is the minimum number n, such that there exists a n vertex graph G. So now there is to prove upper bounds on this, you need to come up with a graph G as well. And to prove a lower bound on this, you need to come up with a coloring of any graph G, such that the following holds. Any two coloring of the edges of G will contain an induced, and I'll say what induced means in a second, monochromatic copy of H. So it means that it's a copy of H with the following property, like a copy of H, such that you have, say, these are edges, and these are non-edges. So if H is this graph here, this is H, I need to find exactly this in G. So this needs to be in G. And so that not only the edges of H need to match up and be all the same color as in G, the non-edges of H also need to match up. And somehow we know much less about, I feel like we know much less about containing induced subgraphs than we know about containing just normal containing subgraphs. And notice that, okay, for the clique, this problem is the same problem as normal Ramsey numbers, but then for any other graph, it's going to be different, other than clique. So now it's not even clear these numbers exist, right? Because it's contingent on the existence of a graph, this graph G. And so this was shown in the 70s that actually this is a well-defined concept. So we can, for any graph H, we can always come up with a graph G, such that no matter how we color the edges of G, there is one of these copies of H that match up not only in the colors, but also in the edges. And I should say here, like for instance, this is, so this is good, but like if I were to take, say, this thing here, say this is blue, and then this is non-edge. This is bad. I don't like this because, okay, you might see that the red edges match up, but then this blue thing should actually be a non-edge. So it's not enough that the non-edges of H are just non-edges in red. They have to be non-edges of G actually. So just an important clarification. So this makes the problem
Marcelo,
harder,
just
right?
a definitional question. Is it safe to think about this as sort of a three coloring of the graph, of blue, ed, and non, of the three coloring of the complete graph?
Yeah, so it's not exactly because you like I choose the non. It is true, like what you said is true, but the only difference I would like to make is that non is special, right? Because your adversary is gonna choose red and blue, and I'm gonna choose none, and then my adversary is gonna choose red and blue. Yeah.
Thank
you.
you.
This is just saying that non is special somehow. And then the conjecture that Erdős made in 75 is actually that this behaves exactly like the normal Ramsey numbers. So these things grow exponentially in K. And so as you grow, you should be growing exponentially in K, but the bounds these works originally gave here were at least double exponential, so they weren't close to this Erdős conjecture. And there was this very nice advance of Kohayakawa, Promo, and Ruddle in the 90s, where they showed this behaves like 2 to the K times log K squared. And then Cohn, Fox, and Sudakov shaved off on factor of log K, and they showed 2 to the K times log K. And then the thing I want to talk about is this work by Aragão, myself, Daya, Felipe, and Marciano, which we show the Erdős conjecture. So we show that this thing grows at most exponentially in K. And the main reason I want to talk about it is because like the proof is fully probabilistic, and we need it doesn't work, like we don't know how to do it constructively. We don't know how to come up with like a pseudo randomness condition in the graph and run the proof. It does really use heavily like the randomness. And the idea is that the graph we're gonna take is just gonna be G1/2, so a uniformly random graph among all graphs and vertices. And we're gonna show it works with very high probability for this graph. And the idea is gonna be, we're gonna do some Erdős-Zakaras type induction, like similar to what Simon showed in his talk. Like you're gonna try to go into some neighborhood in red and then blue and so on. But at each step, instead of doing it like deterministically, at each step, we're gonna reveal the neighborhood of our vertex after we revealed the neighborhood, the rest of the graph in a small place, and we union bound over colorings. So it's gonna be a bit confusing, but the idea is gonna be that we're gonna fix some small set. We're gonna reveal how the graph looks like in the small set, and we're gonna union bound over all colorings of this graph there. And so it's a huge number of possible colorings, right? Because it's 2 to the number of edges of this graph. So to be able to overcome this, we're gonna need to prove very good probability bounds on everything we do. And it turns out it's good. So everything will need to be happening like a large deviation estimate kind of world. And the idea is that you're gonna now reveal how this graph inside U and look at and fix a choice for coloring of GU. And now we're going to be able to apply some kind of induction hypothesis inside there to find some smaller copy of H. So instead of finding a complete H, I'm going to find some H minus, which is H just without one vertex. And now we're going to show that we're going to be able to extend each H minus by some vertex V with probability 2 to the minus K. We're able to do this. So, okay, at this point, I'm not talking about colors. I'm just gonna talk about, how a property of the random graph. So imagine I fix some copy of H minus, which is just H. So H minus is just H minus some vertex V. And now I just want to extend H minus to some vertex V. And then the probability a given vertex extends H minus is going to be the probability that it sends all the correct edges to H minus. So every time it's a non-edge in H, it needs to send a non-edge, and every time it's an edge in H, it needs to send an edge. So the probability this happens is going to be like 2 to the minus K, because this thing, let's say, has K vertices. And then, but the point is that we don't only have one chance to extend each H minus. We have n for each vertex outside. We're going to be able to try n times, and we are not only going to be able to find one copy of H minus inside. We're going to have some strengthening of the induction hypothesis that allows us to find many copies of an H minus inside this world U. And they're going to be very well spread, well behaved somehow. And then the idea is that if you apply some kind of large deviation estimate, you're going to be able to show that the probability no vertex outside extends any of the copies of H minus inside is going to be very, very small, which is going to beat the union bound over colorings inside this. But notice that I didn't mention colors in the extension, right? I'm just saying that, okay, you're going to be able to extend, but without saying like that you're going to be able to extend in the correct color, right? Like I'm just saying that you're extending in the graph. And now the colors, to bring the colors in, we need some other method. Sorry, that's what I said now. And then to bring the colors in, we need this tool, which is this hypergraph containers, which allows us to control subsets of a random set, which has some forbidden structure. And the forbidden structure we should think about here is this extending one of these copies of H minus inside there. This is like the forbidden structure we should think about. And then we should think about these containers as allowing us to control how colorings look like now, instead of just how the behavior of the full random set look like. And this is one of the main things that is hard, like controlling this thing. But we have these nice tools. But the other thing that turns out to be very tricky about this is that I told you the induction hypothesis is like something like, okay, there are like many copies of H minus inside, and they're well spread in some way. And it turns out that if you're doing induction, you need to show that your induction hypothesis would hold for the next step. So we would need to not only find one copy of H, but like a family of many copies of H, which are also well spread. And one of the main things we need to prove to show this is kind of like a containers version of this thing. But even like a large deviation estimate for this type of thing, I think was not known before, as far as I know. And the theorem that I want to show you is this. If you have some hypergraph H, so just like some hypergraph is just some family of sets of size T, and now you take a random subset of its vertex set, where you include each vertex independently with probability Q, then what we can show is that the probability that when you restrict your hypergraph to your random subset, it's not well spread, it's going to be exponentially small. So it's a large deviation type estimate, but not for having edges. Like, for instance, if you wanted to just say that this hypergraph, when you restrict this random set, has a lot of edges, then you would be okay by like kind of by now standard techniques in the field. But saying that not only it has many edges, but the edges are also well spread. So meaning that you don't have like large degrees and co-degrees and stuff. So like the edges are like evenly distributed in your set. I think it wasn't known before, and this is kind of like a large deviation estimate that transfers it says that you can transfer spreadness from the whole world to a random subset with very, very, very good probability. So showing this holds with like probability 1 minus literal 1, I think it's okay by some like type of second moment argument, but showing it holds with like large deviation, then this is like the real thing here that we do. And I think this is and the final thing I would like to say about this is that we use this new type of container hypergraph container lemma that holds for global properties. So like if you have like a global property that is somehow a global decreasing property, this lemma seems like it can somehow be useful for these kinds of things. And this is what we use to kind of transfer like this problem about finding this hypergraph that is very well spread to some like more local thing where we can apply more standard tools. So because like this property about your set being like your hypergraph restricted to your set being very well spread is kind of like a global property of your set. So it's something that's kind of tricky to deal with in principle. And this is all that I wanted to say. Thank you.
Thank you. We're all clapping theoretically. I'm assuming everyone else in the cloud also is clapping. If there are any questions, thank you. We're all clapping theoretically. I'm assuming everyone else in the cloud also is clapping. If there are any questions, thank you. Oh Lord, why is this bouncing back? I'm hearing myself. I hope no one heard that also. Okay. If there are any questions, oh Lord, why is this bouncing back? I'm hearing myself. I hope no one heard
Sorry,
that also. Mute.
maybe
Questions.
my
Oh, great. Sorry about that. Technical difficulties we're having left and right over here. One
We have one
additional
additional
question.
question. Does all this hold in any dimension D?
maybe it's for is this one for Simon or?
I'm not sure. The question about the dimension of the graph. I'm not sure what exactly is being meant here, frankly.
For me.
For you.
Dimensional. Wait. I see. So maybe is the you mean like the uniformity, like the
Uniformity
size
of the
of the
hypergraph, perhaps.
yeah. So yeah, there is some dependence on the uniformity, but the dependence turns out to be quite yeah, it's good in some ways. It's like it's polynomial in the but you need to have some restriction in the uniformity of the hypergraph.
Okay, if there are no further questions, thank you very much to both of the speakers. This was a lovely talk. Again, claps for everybody. And we'll see everybody in the next One World Probability seminar session.
Thank you
Thank
very
you.
much.
Thank you.
Well, thank you very much for the invitation and the opportunity to speak. I think we appreciated it very much as well. Thank you.
Wonderful.
And I think I was to blame for the feedback noise. Sorry about that. Okay.
We will never forgive you.
Okay.
So do we need to turn off the recording?